Today we study ESA18H, a solution of the simple harmonic oscillator 2. The total mechanical energy E of the simple harmonic oscillator is conserved because the equation of motion can be multiplied by the velocity to compute the equation of power. And we have found that this is expressed as a total derivative of the total mechanical energy equals to 0. That means total mechanical energy, that is the sum of the kinetic energy and the potential energy, is a constant of motion. In classical mechanics, the kinetic energy of mass is real. Therefore, x dot square is a positive. X dot. Wait a second. X dot square is a positive. X dot square is a positive. We can find that this either is a positive or negative or 0. So x dot velocity is a real number. Square of a real number is a positive vector. So we call a point at which it changes the sign of the velocity to be the turning point. If a particle is at a turning point at time t1, so at time t1 the velocity becomes 0, and it crosses, so the positive and negative. This is a velocity. At turning point, velocity is 0. If the velocity is 0, then the kinetic energy disappears. Therefore, the total mechanical energy is simplified to be the 1/2 kx squared. We call A, that is the value of the displacement from the equilibrium position at the turning point. Then, this is called amplitude. Amplitude. We recall that the sum of the potential energy and the kinetic energy, this is a constant motion. What happens if I substitute the 0 for this x? That is, at the equilibrium position, the potential energy vanishes. Then the kinetic energy is exactly the same as the total mechanical energy. The value of the maximum value of the velocity can be computed by making use of this identity. We know the total mechanical energy is identical to 1/2 k amplitude squared. We can substitute this for the energy E. Then we remember omega 0 squared equals k over m. So k equals m omega 0 squared. So we substitute omega 0 squared for this amplitude A, the spring constant k. Then the maximum value of the kinetic energy can be expressed like that. We find this 1/2 mass, they are the same. So maximum value of the velocity squared is omega 0 squared multiplied by the a squared, amplitude squared. The maximum value of the speed should be omega 0 a. Because the velocity is a real number, if the motion is restricted to in one dimension, the range of the position is between the amplitude and negative value of the amplitude, the velocity squared. Therefore, the velocity of the mass is in the region minus a omega 0 to a omega 0, plus minus a omega 0. In general, any arbitrary value of x can be substituted and the total mechanical energy is conserved. We move this kinetic energy term to the right side and multiply the reciprocal of this over factor, 1/2 m. So 2 over m, open the brackets, e minus 1/2 kx squared. We remember the total mechanical energy can be expressed in terms of the spring constant and amplitude. So we factor out this common factor to reach the point that in addition a squared, we have k over ma 1 minus x squared over a squared. K over m, that is omega 0 squared. We have factored this out, ka squared. Therefore, velocity squared is omega 0 squared, a squared, 1 minus something. We recall that the range of this displacement from the equilibrium position, x, is between plus minus a. Therefore, x over a is between plus 1 and minus 1. So it is convenient to define the scaleless displacement that is called c, x over a. Then this expression is a little bit simplified. X dot should be a c dot. So we divide both sides by a squared to find the expression for the scaleless variable, scaleless displacement c, like that. The c is in the region between minus 1 and plus 1. So this one, 1 minus c squared, varies from 0 to 1. Why don't we take a square root of this? So velocity squared, right side is positive definite, but left hand side is positive definite too, but c dot is either positive or negative. So depending on the situation, if the mass oscillates like that, mass m oscillates in the region, and this is equilibrium position, the motion from minus a to plus a is x dot is a positive. The motion from plus a to minus a, x dot is negative. So depending on the situation, we attach a plus minus sign as an over factor, and we take the square root of the right hand side. Then this is c dot, that is the first of the time derivative of the scaleless variable, scaleless displacement with respect to the time. As a result, we separate the numerator and denominator in the Leibniz notation for the first order derivative. Then we find the differential of time can be expressed in terms of differential of displacement, depending on the sign that can be classified
based on the motion from minus a to plus a and motion from plus a to minus a. Now we can make use of the trigonometric relation. Differential of sine is cosine d theta. Cosine theta is square root 1 minus sine squared theta. Therefore, we will remember, if we restrict ourselves to be the region in the positive, cosine theta is a positive definite. In that case, we don't have to consider the sine. So we defined arc sine function, that is an inverse function of sine theta. The sine theta is replaced with xi. Then we find that this is dxi equals 1 minus sine theta, xi squared, d theta. Okay? Therefore, dxi over square root 1 minus xi squared is d theta. So we can integrate both sides. Then it is nothing but the theta minus the theta 0 initial value of the angle. Because this one is equivalent to theta equals arc sine xi, our final result for this integral is arc sine. For a special value from the integral from the equilibrium position to the maximum point at x equals a, that means xi equals plus a plus 1. Then arc sine 1 subtracted by arc sine 0 is half a pi. We recall that sine half a pi equals 1, sine 0 equals 0. From this relation, the time interval for the motion from minus a to plus a, then is xi equals minus 1 to plus 1, corresponds to the integral of time with the value xi dot is a positive. So xi equals minus 1 to xi equals plus 1. The integral gives this integral from this leftmost to the rightmost point, the two turning points, the motion between the two turning points from the negative value of x and positive maximum value of x, minus a to plus a. This is just symmetric. So the period of motion is t, capital T, then the motion from this point to that point is 1/2 t. The motion from this point to that point is 1/2 t, to make the sum to be the period capital T. What we can find from the motion from minus a to plus a is 1/2 of t. So according to this relation, we have 1 over omega 0 from the value of xi equals minus 1 to plus 1. We integrate over xi and we make use of this relation. This is arc sine. We know this integrand of this integral is an even function. Therefore, the integral from minus 1 to 1 is minus 1 to 0 and 0 to 1, and they are the same because this integrand is independent of sine. Therefore, these two integrals are identical to each other. So we have factor of 2. So lower bound is replaced with 0, and we have multiplied this expression by a factor of 2. We recall that the integral table for the arc sine evaluated from 0 to 1 is 1/2 of pi. 2 cancels, and left hand side we have 1/2 of t equals a pi over omega 0. Therefore, we have the period is 2 pi over omega 0. That's it for today. Thank you.